Okay, today we're going to look at natural logarithms and trigonometric applications. I just honestly think we do this to confuse you guys. So let's just write down some goals. Goals are always good things to have. So we'll learn what is the natural log. Change that to a nice blood red. Yeah. So we'll learn what is natural log. We'll learn notation for natural log, mm, where it came from. I think that ought to do. And we will solve a few problems with natural log. And we'll graph a few functions. That ought to just about do for our goals. Okay, let's first just kind of look at where natural log came from. So natural log is kind of a number like pi. So pi is a famous number, it's an irrational number, and it comes up a lot in circles and in, well, a bunch of other things. Um, there is another number which ends up having a lot of practical uses, although I actually looked into the history and initially nobody really cared, surprisingly, about natural log. It came about in the 1600s and didn't really become popular until a guy named Euler came up with the notation for natural logs. And I am well aware that Euler is spelled Euler, but it's pronounced Euler. And it came about when this guy was examining this limit. This formula may not look very familiar, but it actually turns out that this is your compound interest formula with a couple modifications. And this isn't super important, but it is nice to know, like, where did this thing come from. So I think it was Euler. He was looking at continuous interest or continuous time. So the reason why they don't look the same is he said, well, if time goes off to infinity, so we can kind of just get rid of it, and gets compounded continuously, so that's why n is going to infinity, then the rate just kind of goes to 1, and he was examining this limit. So when n gets really, really big, so if you start plugging in bigger and bigger and bigger values for n, he was curious, what is the value of this limit? And well, what's going to happen is this n, when it gets really big, you're going to get 1 over a really big number, so you're essentially going to get 0. Okay, but as you get bigger and bigger and bigger, you are raising this number to n, so you're getting 1 plus a tiny little number raised to the same number that n was, and it turns out that this limit ends up equaling approximately 2.718, and we call this number e, and that is probably after Euler, because his name started with an E. Mind blown. That's your mind blowing up. Kind of looks like a muffin. Okay, so basically this number came about from this limit. It originally came from the compound interest formula. That's the problem it was originally applied to, and it has a value of 2.718. It's kind of good to remember the first couple digits of this number. You can find it on your calculator. So your calculator will have a button that says e to the x, and there will also be another button that looks like this. This is pronounced ln or ln. Okay, and this, well, we're going to talk about that in a second. So let's flip the page. So yeah, let's talk about that. Let's write a title. So what is the natural log or logarithm? Okay, so the notation for the natural logarithm is ln. And what is it? Well, um, if we use e as a logarithmic base, then we have y equals log in base e of x. Okay, so just like how base 10, we don't really write the base for base 10, we just say log of x. Um, the log that has a base of e is called the natural log. So we call that the natural log, and it is so frickin' special that we gave it its own button on the calculator, and we just write ln of x. So ln of x is the same thing as writing log in base e of x. It is just so special that we give it its own name, and it's called the natural logarithm, okay? And once again, this is all coming from that Euler guy, okay? So he made this all up. This is his fault. Unfortunately, he's no longer with us, so we can't make him suffer. But you can type in on your calculator, you can type in ln 10, and if you do that, I get 2.3. Okay, and let's just think about what this means. Okay, so ln 10 is just log in base e. Okay, so to prove it, let's just write that down for a second. So ln 10 is log in base e. Okay, so all that means is just like a regular log, it just means that if we take e and we raise it to some power, when does it equal 10? Okay, well when you plug in on your calculator ln 10, you got 2.3. So that just means that e to the power of 2.3 equals 10. Okay, and you can go and you can try that on your calculator. So there should be a button that has an e to the x, and you should be able to plug in e to the power of 2.3, and you should see that you get 10. Okay, so it's exactly the same as writing this log e of 10 equals some number. It's just that instead of log e, we write ln, because log in base e is called the natural logarithm. Okay, so really this is actually nothing new. So e and ln x are just like any other log. So all the same laws that we learned for logs apply to ln. So that means that your product law, your quotient law, your power law, all those things are identical for the natural logarithm. The only difference is that the natural logarithm has base e, whereas other logs have whatever base it says. Okay, so we can graph these things. Nothing really changes for graphing them. So let's try to graph this one here. Um, this doesn't come up too often on the exam, and I'm starting to just kind of speak a little quieter because I don't want the exam people to hear me, but just in case it ever does, make a table of values, and you can plug in x equals 0, and you're gonna get anything to the power of 0 is 1, so we're gonna get 1 plus 2, so we get 3, so we can go ahead and graph that point. There it is, 0, 3. If you plug in 1, you're going to get, well, e to the 1, which you can evaluate on your calculator, because who wants to go 2.71 to the power of 1 plus 2? Okay, so it's going to approximately be like 3.7 or something. Okay, but you can just label that point, 1 for x, and then you can just label it up over here somewhere. And as long as you label it, you're okay. So that's the point 1 e plus 2. Okay, and let's think about our y asymptote. So this is just like any power function, except there's a transformation here. We have the plus 2. So instead of having the horizontal asymptote down here at y equals 0, like most power functions, this one, well, it got shifted up 2 units. So that asymptote is actually, I'm going to do it in green, it's actually right there. Okay, and now we can see what this graph looks like. Looks like that. So it looks like a power function. So we can graph that, that's no problem. Let's try another one. So we have y equals ln of x plus 2. Hey, no sweat. we can just make a table of values. Okay, and we know that ln behaves exactly like logs. Okay, so just like logs, the argument can't be negative. I think that font size is a little too big. So no negative arguments. And that's just like log. Okay, so all the rules you know for logs apply to ln. Okay, the only difference, and if I haven't said this enough, I'm going to say it again. The only difference is that ln has base e, logs don't. So let's try plugging in some numbers. So if we plug in, and remember, this can't be 0. So right off the hop, you can find your vertical asymptote by asking yourself, well, what x value is going to give you 0 in here? And the answer to that is -2. So your vertical asymptote is x equal -2. So we might as well graph that. Okay, so there is my vertical asymptote. And now I'm just going to say, well, let's plug in x equal -1. Well, if you plug in -1, you're going to get ln -1 plus 2. So you're going to get ln of 1. Okay, and well, you can plug that in on your calculator just for a second, and you're going to get 0. Let's try plugging in x equals 0. If you plug in x equals 0, you get ln 2. Now, if you plug that in on your calculator, you get approximately 0.7. Okay, nobody's expecting you to memorize this. This would only ever come up on the calculator part of the test, if it even does. Okay, so we can graph the point -1 for x and 0 for y, so we're right here. And then we can graph the point 0 for x and approximately 0.7, so we have to label it. Okay, so that is our all important y-intercept. So we should label 0, use the exact value ln2. Okay, and we know that this is going to look a lot like a log function because they're essentially the same. And in fact, this is looking like our log function. I'm not surprised the asymptote got shifted 2 units to the left. Okay, so it's just going to curve down, it's going to hug that asymptote, and then it's going to just slowly increase like that. Okay, so it looks very much like log of x plus 2. Okay, very, very much the same. I think I covered everything there. We can just ignore that for now. Writing the inverse right, I just said we would ignore it. There. Alright. Flip the page. Okay, so now I'm going to share some important values to just know. Okay, so I'm going to put important in quotation marks. So some important values to remember for ln. Just trying to make this look pretty. It's not working. Oh, there we go. Okay. So, and we kind of know this from log. So our log background allows us to discover a very useful piece of information. Hooray, I can't wait. We know that log of base 2 of 2 to the 3 is 3, right? And that makes sense because we're just saying, well, hey, 2 to what power equals 2 to the 3? And the answer is, well, x equals 3, so that equals 3. If you have log in base 10 of 10 to the 7, same logic, right? So 10 to what power equals 10 to the 7? The answer is 7. Okay, so what if we apply this idea to natural logs? Well, ln of e to the 5 is equal to 5. Why? Well, ln has base e. We don't write that, right? Because it's like base 10 for this log. It's just we know that's what it means. So if we go e, because that's the base here, so e to some power equals the argument e to the 5, it makes sense that this equals 5. So my question, and this is the thing that you should remember, I mean, this is good to remember, but this is really important to remember because this will come up possibly on the non-calculator part of the test. ln e is equal to what? And I'm waiting for Youpei to answer. No answer. Answer, Youpei. Just kidding. I'm sure that he was thinking 1. Okay? Why? Just to make sure. This is base e, so e to some power has to equal the argument, which is e to the 1. So x equals 1. Just make sure that you remember that. You're going to use that a lot of times. Okay, I'm going to put a lot of check marks. There is one other thing that we need to add here that also comes up quite frequently. So here we go. Let's also note that e to the power of ln of x equals, and here's a drum roll, equals x. Okay, that is just a very useful one to know. You will need it a lot for when you are solving equations that have the natural logarithm in it, okay? So if you ever have e to some power that has ln in it, the answer is going to be whatever the argument is, okay? So the answer is the argument. So in this case, the argument was x. So just to do one more example, if I had e to the ln of x plus 2, the answer here would be x plus 2. Alright, and for very similar reasons that this is 1, this is x plus 2. Alright, we are finally ready to try some questions here. So, just remember, all our rules for logs are exactly the same for ln. So, okay, all those rules apply. So let's just try a couple questions. So if you have to expand ln of this stuff, again, all the rules apply. So here we have division, so we can break it up and write it as a subtraction sequence. So we can write ln of x squared times y to the 3 subtract ln of the square root of z. And then this thing here, well, that's just a product, so we can split it up and write it as addition. So that is ln squared, or ln of x squared plus ln of y to the 3 minus ln square root z. We have to simplify the square root. So the square root is z to the 1/2. Okay, and then we can bring the 1/2 down. We can use the power law and just rewrite it like that. And I can recopy everything else. Alright, wonderbar. Here's a question where we are writing something as a single natural logarithm. Okay, so again, work left to right. Actually, before we do that, I'm not really thinking today. If you have any, numbers in front, so something that's multiplying the ln, we can use the product law. So we can go ln, lots of writing. So we can bring the 3 up. Same thing on this one, the 1/3 in front is a power. Okay, now work left to right. Okay, don't make the mistake that I was making. Work left to right, so we have addition. We can write that as a product. So using ln x minus 1 times x plus 3 to the power of 3. Okay, I'm going to do this all in one step. Then I'm going to have this subtract, this thing here. So I'm just going to go ahead and write it in the denominator. So I'm going to need some really big brackets. I'm going to use some nice square ones. I'm going to write denominator. Here it is. It's ugly. It's bad. But whatever, that's what it is. Okay, and I'm just gonna make this look a little prettier, a little bit more symmetrical, write a bigger ln. Okay, so ln of all this stuff, we did it, we wrote it as a single logarithm. Okay, let's try solving a couple equations now. Here we go. Well, this looks like a barrel of fun. Okay, let's go. So there's obviously no easy way to rewrite this thing over here with a base of 3. So this is a case where you have two options. You could do what we were doing in 5.7. You could apply log to both sides, okay? Or you can apply the natural log. It doesn't matter which one you use. So we can use log. They're specifically asking us to use the natural log, so we'll do that. But we can get the same answer anyways. So I'm going to apply ln to this side. So I'm going to get ln 3 to the power of x equals ln of all this stuff. So I'll use square brackets. Okay, and now I can start solving. So I can split this up, right? It's a product. So I can write ln2 plus ln of 5 to the power of x plus 4. I'm going to recopy my right hand side. Well, actually, I lied. I'm going to use the power law and bring the x down in front. Okay, and I'm going to do the same thing on the right hand side now. So recopy the left hand side. Recopy the ln2. I'm going to bring that x plus 4 out in front. There we go. Yeah, and now we can distribute the ln5 into the brackets. This is just one of those questions that is a barrel of fun. So of course I'm going to put it on your test, but only because it can come up on the exam. Alright, so I think I got that all expanded out. Going to recopy this side. Okay, so now it's our favorite time. We get to move everything that has x over to one side. So I'm going to move this thing over here. And then if we had anything over here that didn't have an x, we'd move it over. In this case, we don't. So here we go. Going to recopy. We got x times ln3 subtract x times ln5 equals ln2 plus 4 times ln5. Gonna pull the x out here. Okay, I suppose I'll write it. So I'm gonna have ln3 minus ln5. Oh, so much rewriting. This is so boring. Oh, alright. We can divide both sides by this. And I'm just going to get a little bit lazy here. Please, 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 please never do this. Recopy it, but I'm not going to. So I'm just going to cross these out because that equals 1. So now I have x equals this. That's my final answer. Please forgive me for not rewriting it. Oh, you know what? Plug it in on your calculator. You might want to pause the video here. Plug this in. See if you can get an answer for x. I got negative 13.959. Alright. Alright, I just drew over my 9. Who cares? Okay, here's another one. We saw ones like this for logs. Okay, if you have ln on both sides, move it over. Move it over to one side. Okay, so what I mean, this is just terrible broken English. I don't know what's going on. Move this over to, say, the left-hand side. Doesn't really matter. Pick something and do it. That's what my mama used to say. So we're going to move it over to the left-hand side. Okay, now that we have it like that, we can combine these two ln's, right, using our quotient law. Okay, and now that we have just one ln, we can write it in, and usually Ben answers this question, we can write it in exponential form. Okay, so, oh, geez, what's the base of ln? Oh, yeah, it's e. So it's e to the power of 1 equals the argument. There we go. Now we can multiply both sides by x. to get x times, e to the 1 equals x plus 1. What was e to the 1 again? Wasn't that one of those things? I can't remember. Let me look at my notes here. E to the 1, right. Silly me. E to the 1 is 2.71, right? So we're just going to have to move everything over to the same side. So I think I'm actually going to move everything to the left-hand side. So I'm going to subtract x, and I'm also going to subtract 1 from both sides. So I'm going to get x times e, and then subtract x, subtract 1, and don't forget to write on the right-hand side we have 0. Okay, now this is looking really, really ugly. I would like to solve for x, so I actually kind of made a mistake. I should have left the 1 on this side. So what I'm going to do is I'm going to add 1 to both sides. And this does kind of look weird with the e there. You just got to remember that it's a constant. So I can pull out the x, and I'm going to get e subtract 1 equals 1. And I'm almost there. Remember, this is just a number. I know it looks funny. Okay, so I can divide that out, and I will rewrite this to avoid confusion. So I get x equals 1 over e subtract 1. And you could plug that in on your calculator and get a number, or better yet, just leave it exact. Alright, that one was weird. I'm going to write weird. That was weird. Kind of write a funny face. Kind of looks severe. Alright, let's just do the next question. So, 2 last questions. We're going to solve for t in this one, and something special is happening here. You will never solve this one unless you remember that thing that I told you to remember a few pages ago. So let's go back. Too far. Oh, not far enough. Here we are. Okay, so this is the rule I'm talking about. You must remember this. Okay, so if you ever have e to the power of ln, remember that the answer is whatever the argument is. So I have e to the power of ln. So remember that the answer is just going to be whatever the argument is. So I can immediately write this. And you don't really need to give any explanation. You can just write that. And boy, that's easy. So I'm going to get t equals 3. And if you happen to have your calculator, you could verify. But if they ever gave you this, it would be on the non-calculator part. So now we have another one. It looks the same, but there is a small difference. This one does not have ln over here, so it's just e to this power. Okay, so here we can apply ln to both sides. And before I said you can use log if you want, but here's the thing. If you have e, you're better off applying ln, because when you apply ln to both sides, you're going to get ln e to the power of 2 minus 1 equals ln 5. Okay, by applying ln, you now can use this special rule from before. Because ln is in base e, and this is e to some power, it just works out that your answer is going to be this. Okay, so if you see e's in your question, apply ln, because maybe something will cancel like that. Otherwise, you can apply ln or log to solve. They both work pretty much the same. So now we can solve. So our answer will look a little different. So when you figure it all out, you're going to get ln 5 plus 1 divided by 2, and that is what t is. And we are done. Thanks for joining me for these notes. Not sure if there actually are supplementary questions. Oh no, those don't exist anymore. So just do the homework. You should have homework in your book for section 5.8, and we are actually a day ahead now because the other classes are going to miss today because of the the Grade Wars in Period 3. So we are a day ahead. So yay! Okay. Bye bye.